So we want to talk about u substitution with definite integrals, because the integrals that we have used u substitution for so far are indefinite, so they don't have boundaries. So the question is, what do we do when it has boundaries? What do we do when it's a definite integral? And there's really two ways that you can do it. So the first method is you can just do the u substitution. You could take the integral without the boundaries, perform the whole process, and at the end, then when you replace u back with x, then put in the boundaries. Okay, so that's what it means by perform u substitution without the limits and then substitute them into the result. Or the other method is you could actually change the limits on the integral to reflect the substitution that you've made. Okay, so those are the two options. Now we'll talk about each one and I'll show you what I mean by those things, but you can kind of separate them. Method one says just do the integral. Don't worry about the fact that there's limits there. And then at the end, when you've done u equals something, you've plugged u in, you've integrated, you've got everything in terms of x again, then plug the limits in. And the other one I think is probably more efficient, but sometimes it's a slightly more confusing method to some people, where you actually, when you set u equal to x squared plus 3, if x is 5, then you go 5 squared plus 3, and that's what your u value is. So I'll show you both. So here's an example. Okay, we did this before when I showed you u substitution. So we know this is the substitution, u equals x squared plus 1, and du is 2x dx. So what you can do in method one, if you look at what we're doing here, there are integral limits. It's going from 0 to 2. So we have to either, in method one, say, okay, imagine that those aren't there for a minute. So we drop the limits. We make the substitution. Okay, so our substitution is u is x squared plus 1, du is 2x dx, so that means that dx, which and x that I'm trying to replace, x dx, I'm going to replace with 1/2 du. So I get 1/2 u cubed du. I integrate. So if I integrate u cubed, I get u to the 4th over 4 plus c. Then that becomes u to the 4th over 8 plus c. So this is all assuming that the boundaries just aren't there. Okay? And then I replace u. So I get this. Okay, I get x squared plus 1 to the 4th, over 8 plus c. So I know the indefinite integral. And then what I do is I say, okay, now imagine that their boundaries are now back. Then the integral just becomes that, without the plus c, from 0 to 2. And then I plug in 2 with the fundamental theorem of calculus, right? We just plug in the top boundary, the upper boundary, upper limit. So 2 squared plus 1 to the 4th over 8, and then I put in the lower boundary. So 2 squared is 4, 4 plus 1 is 5, 5 to the 4th over 8 is 625 over 8, and then 0 squared plus 1 to the 4th is 1 over 8 is 1/8, and we just subtract them, we get 624 over 8, and we get 78. That's what 624 divided by 8 is. All right, so that is method one. And method one says, just pretend the limits aren't there, integrate, and when you're done, then plug the limits in. Method two says, don't do that necessarily, make the substitution. Okay, so we're going to make the substitution, but also make the substitution with the boundaries. So in other words, we're going to say u is x squared plus 1. So let's figure out when x is 0, what is u? That's what we're trying to figure out. And then when x is 2, what is u? So we plug in 0 into our substitution, into here, because we said u is x squared plus 1. So when x is 0, we get 0 squared plus 1. That means when x is 0, u is 1. And then we say, okay, well, what happens when x is 2? So 2 squared plus 1 is 5. And then what we do is we integrate the substituted values, but we also substitute the limits. So we make the substitution. This is going to become du over 2. This is going to become u cubed. And instead of going from 0 to 2, we say, let's go from 1 to 5. So we actually change the limits to reflect the substitution. And then what that does is it allows us to take the integral and plug in 1 and 5 right away. So we don't have to go back to x. So we go half of 5 to the 4 over 4 minus 1/4. That gives me half of 625 minus 1 over 4, which is the same answer. It's 624 over 8, which is 78. So we get the same answer either way. So either method works. This method, though, allows us to stick with u. We don't have to go back. So we don't have to substitute the x back in because we've changed the limits now. So we're saying this is the values of u, these values, 1 to 5. So I like that method better, but either way works. And you can make the decision about what you do in terms of how you integrate. You can either integrate, then plug the limits in, or you can change the limits to reflect the substitution. Okay, so let's just do another example of this one. So we have e to the 2x minus 1, so we're going to let u equal 2x minus 1 because that's the composite function. It's e to that power. Then du becomes 2 dx. So we get half du. Now, the first method would say, okay, now integrate without changing the limits. Essentially dropping them completely. Like, so pretend they're not there. And then do the integral and then plug them in at the end. So we would go let's pretend the limits aren't there. We'd get a half out here and e to the u du. So the integral of that is e to the u over 2 plus c, which would give me e to the 2x minus 1 over 2 plus c. And then we would say, okay, now this then is equal to the integral from 0 to 1. Sorry, not the integral anymore. We've integrated. This value, e to the 2x minus 1 over 2 from 0 to 1. And then you would plug in 1, so you get e to the 2 times 1 minus 1 divided by 2. And then you go minus e to the 2 times 0 minus 1 divided by 2. And I apologize that it's kind of cramped. But then you would get e to the 1 over 2. And here you get e to the minus 1 over 2, which would give you e squared minus 1 over 2e. Okay? And that's our answer. So that is the way to do it. That's method 1. It's saying assume that the limits aren't there, and then once you've got your result, then say, okay, I know the integral of this is now this, and I plug in 0 and 1. The second method is to say, when we make this substitution, what is x and what is then u based on that x? So I'm just going to erase this so I have some room to write. But the second method would say, okay, don't go back to x, but say when x is 0, what's u? So u would become 2 times 0 minus 1. So u would be minus, would be minus 1. Fix that up here. And then the other limit is 1. So we say when x is 1, we go u is 2 times 1 minus 1, so u is 1. So we make the substitution, but we also substitute out the limits. So the limits go from minus 1 to 1 now. And then when we integrate, we get e to the u over 2, just like we did before, but now we're plugging in directly minus 1 and 1. So if we plug in 1, we get e to the 1, which is just e. And if we plug in e to the minus 1, we get 1 over e. And we end up with the same result. We still end up with e squared minus 1 over 2e. Right? If we get a common denominator here, that's what we're doing. So we're just multiplying that by e to get e squared minus 1 over 2e. So either way it works. Either method works. The second method is more efficient. And so it will save you time. And particularly when you get into bigger questions or longer questions, if you can save a little bit of time on things like that, it will make your life easier. Now, are you doing less work? Not really, because you're still figuring out what u is when x is a certain number. So you're still doing the same calculation, but it's almost just the order that you're doing them in is slightly different. All right, so hopefully that concept makes sense, what we're doing there. The u substitution is the same as it always was. The actual making the substitution is just a matter of what do you do with the limits. Check our time here. So we better leave it there, but hopefully that makes sense, and we will do more examples together in class.